Hello everyone, this is November 6th, part 2. We are going to be starting today what's called antiderivatives, which we have spent our semester really in preparation for this section and integrals going forward. So this is the part that deals with some area problems, and we'll get into some of the applications and some of the uses a little later on. But for today, we're going to be working on the basic mechanics of finding an antiderivative. So what is an antiderivative? A function f is an antiderivative of small f on an interval if f prime of x is equal to f of x for all x in that interval. So for example, what we're doing is we are doing a derivative in reverse. So if, for example, I have f of x equal to 3x squared, then my big F would be the function that this came from, 3x squared came from as a derivative. Well, we know when we take the derivative of something, we bring its power down to the front and reduce its power by 1. So if I were to envision how we got to 3x squared, we got to 3x squared by dropping that 3 down and reducing the power to 2. So an antiderivative of 3x squared would be x to the third power. Also, if I started with, say, 4x to the third, well, you notice that 4, if we drop down 4 from a power, we reduce it by 1, we get 3. So one possible antiderivative of that function would be x to the fourth. If I have, say, 5x to the fourth, then bringing the 5 down from the top, reducing the power by 1, means that what I could have started with before we take the derivative would have been x to the fifth. So if I have 6x to the fifth, then really we started with x to the sixth and so on. But I say that these are one possible option for an antiderivative. That really means there could be more options. So let's take this first one, for example. I could have started with f of x is equal to x cubed plus 8, for example. Well, if I take the derivative of that, f prime, then what I get is 3x squared, which is what I need. The derivative of 8 is 0, because it's a constant, it goes to 0. What if I had instead f of x is equal to x cubed plus 11? Same story. So if I take the derivative of that, then I get 3x squared, and my 11 goes away. So the reason that we say that it could be any antiderivative is because anytime you add a constant, when you go to take the derivative of that, the constant always drops off. Now, we can't tell if there was a constant on the original function or not. So what we'll be doing is when we're looking for antiderivatives, what we'll add on to each one is this term called plus c, and that means that there could be a constant, we just can't tell. So if I were to write the antiderivatives of all 3 of these functions, they should all have a plus c on them, because I can't really tell if there's a constant in the original function or not. We'll go through some later on that we can tell, but for now, these ones we can't. So we can add any constant since the derivative of a constant is always 0. So that constant will always drop away. Now, as far as notation is concerned, the collection of all antiderivatives is called the indefinite integral. So the indefinite integral is this particular sign. This means to take the indefinite integral with respect to x is this notation dx. So whatever is in between is the function that you're looking for the antiderivative of. So for example, if I were to, wow, that's a terrible integral sign. So for example, if I were to try and find the derivative of some of the antiderivative of some of the things we've used already, the antiderivative of 3x squared dx would be equal to x cubed plus c. So we don't know what we would have as far as a constant is concerned, but we know that the antiderivative of 3x squared, the thing that got us the derivative of 3x squared, is equal to x cubed. Now for here, we're going to be looking to find the function whose derivative we have. The integrand is the function. That's this right here. This is the integral sign, and the variable of integration is this dx part. So that tells us what variable to take the integral of. Some rules going on. If you have a constant, so if something has a derivative of a constant, it's always that constant times x. So for example, if we have 3 dx, which means integrate 3 with respect to x, this is always going to be 3x because the derivative of 3x is 3 plus c. Now if you want to check your work, then what you want to do is take the derivative of what you end up with. So if I were to take the derivative with respect to x of 3x plus c, then what I get is 3 from the first term, and my c drops off because it's a constant. So this is the correct thing. And we're going to learn a couple more rules today, but we've been using one kind of intuitively already. So let me turn the page. So for the power rule of integration, for all powers not equal to -1, if I have the integral of x to the n power dx, it's 1 over n plus 1 times x to the n plus 1 plus c. So if we were to try and work some of these, say we want to work with x squared dx, then this is my n equal to 2, so I get 1 over 2 plus 1 times x to the 2 plus 1, n plus 1, plus c. If we simplify that, I end up with 1/3 x cubed plus c. Now, until you're really confident, you should always take the derivative in order to make sure you're right. So for checking, the derivative with respect to x of 1/3 x cubed plus c would be equal to, bringing our power down to the front, 3 times the third gives me 1, so I end up with x squared, and my c drops off and gives me 0. So that is my derivative, and that is correct. Now say I wanted to do a different power, say the antiderivative of x to the 5th dx, with respect to x is dx. Same kind of thing, so I end up with 1 over 5 plus 1, x to the 5 plus 1 power, plus c. So 1/6 x to the 6th plus c. Taking the derivative of that, six times 1/6 gives me 1, so I end up with x to the 5th, and my constant drops off. So that is correct. Now we can work with e to the x as well. So if I am looking for an integral involving exponentials and logs, if we're taking the integral of e to a constant times x, then we get 1 over that constant, e to the kx power plus c. So for example, if I wanted to find the antiderivative of e to the 4x dx, then it's equal to 1/4 e to the 4x plus c. As far as a check, if I want to take the derivative of that, eraser. Taking the derivative of 1/4 e to the 4x plus c. Now, when I take the derivative of something that involves e, remember I get that same thing back times the derivative of the power. So 1/4 is tagging along for the ride. I get the same thing back, e to the 4x, times the derivative of 4x, which is 4, and my c drops off, cancels my 4's, and I get e to the 4x, which is what I was finding the antiderivative of. As far as the log function, if I am taking the derivative, or the antiderivative, of 1/x dx, then this is equal to the natural log of the absolute value of x plus c. Now I want you to note the absolute value part. It's only necessary if there's no domain restriction on your 1/x. So 1/x can have any number except for 0 in it. The natural log can only have numbers that are positive. So if there's no restriction on your original function, you have to tack on these absolute value bars just to control for negative numbers of x. So keep an eye on that. But if we were to take the derivative of the natural log of x plus c, natural log derivative of that gives me 1/x times the derivative of the power, or times the derivative of the argument, which is just 1, and our c drops off. So that is what we're looking for. Now I want you to note just real quick that this thing here is x to the -1 power, which is why you cannot use x to the -1 power with the power rule. It's a special derivative that actually becomes the antiderivative that becomes the natural log. So just be on the lookout for that one. Now as far as our trig functions, if I have a derivative of sine of kx, then that had to have come from negative cosine of kx. So when you're taking the antiderivatives of your trig functions, it is similar to when you were taking the derivatives of the trig functions, but you have to be careful of sine. So remember that when we take the derivative of sine, we get cosine. When we take the antiderivative of sine, we get negative cosine. So these are our integrals of trig functions, and these ones you will have to have down. So if I have the antiderivative of secant squared, what I get is tangent. And these all have a multiple of k just in case you have something other than just x in the argument. If my antiderivative is secant tangent, then that was the derivative of secant. So since the derivative of secant is secant times tangent, the antiderivative of secant times tangent is secant. The antiderivative of cosine is sine because the derivative of sine is cosine. The antiderivative of cosecant squared is equal to negative cotangent because cotangent, the derivative of that, is negative cosecant squared. If you are dealing with cosecant cotangent, then what that started as is cosecant. So if you start with cosecant of kx, then the derivative of that is negative cosecant cotangent, so you pick up a negative in the reverse way. If you're doing inverse trig functions, if you start with something that looks similar to these, then you should be thinking inverse trig function, and we'll practice some of those on Thursday. One other rule is that if you are taking the derivative of something with a constant in the front, you can pull constants through the integral symbol. so you can bring it out to the front. You can also split terms whenever you have plus and minus. So if you have a plus or minus in there, you can split them up. All right, let's practice a couple. So lots of rules, but really we're thinking about what thing gives us that as a derivative. So what function gives us whatever we have as a derivative? So if I want to take a look at this particular indefinite integral, then we have the rule that we can split things up. So I'm going to split this up into 3 pieces, and we'll deal with each piece individually. Okay, so that means that I have the antiderivative of 5x squared dx minus the antiderivative of 3 over x squared dx plus the antiderivative of 7 over x dx. Now I'm going to bring the constants out to the front so we can look at just the powers of x, or whatever we have for our function. So if I have the first one, that means we have 5 times the antiderivative of x squared dx, and we're going to be dealing with a straight power rule here. Second one, minus 3 times the antiderivative. I'm going to bring that x squared up to the top. So here it's x to the negative 2 dx. And bringing the 7 out to the front as a constant, 1 over x dx. Note that 1 over x thing is our natural log. So we're going to end up with a natural log for that third. So then when we take our antiderivative here, our 5 is here. Now we're going to bump that power up to 3. So I have times 1/3 x cubed, that's my n plus 1, minus 3, and we're going to bump that power up by 1, so we get negative 1. So 1 over negative 1, x to the negative 1, plus 7, and we have the natural log of x plus c. Now I want you to note we only need 1 plus c. We don't need multiple plus c's, because a constant plus a random constant plus a random constant plus a random constant gives us another random constant. So you don't have to put in 1 for each one, just 1 for the whole problem. So cleaning this up, 5/3 x cubed. We have negative twice, so this becomes plus, plus 3 x to the negative 1, or x on the bottom, plus 7 natural log of x, plus c, or 5/3 x cubed, plus 3 over x, plus 7 natural log of x, plus c. And you should take the derivative of that just to check it. Now if we look at something a little bit more complex, then I still want to split it up into pieces. I'm going to bring the constants to the front. I'm also going to express these powers as some fractions so that we can take the antiderivatives. So doing all of that kind of maintenance work to get started, 3 out to the front, antiderivative, square root of x is x to the 1/2 power dx. And plus the antiderivative of x, we've got a 2 on the top, a 3 on the bottom, but they both came from the bottom, so x to the negative 2/3 power dx. And then minus 6, antiderivative of e to the 3x dx. All right, so now I'm dealing with the power rule for 2 of the pieces, and then I have an e for the third piece. So remember, e gives us 1/3 e to the 3x plus c. So when we get there, we'll have to tack on that 1/3. And working on this, 3 is along for the ride. If I bump up by 1, I have x to the 3/2 power. So 1/2 plus 1 gives me x to the 3/2. So 1 over 3/2 x to the 3/2 plus negative 2/3 becomes positive 1/3. So 1 over 1/3 x to the 1/3, and minus 6, 1/3 e to the 3x plus c. Cleaning this up. All right, fraction-wise, dividing by a fraction is like multiplying by the reciprocal, so flip each one. So I have 3 times 2/3 x to the 3/2 plus 3 x to the 1/3 minus 2 e to the 3x plus c. And last cleanup, my 3's cancel, and I end up with 2 x to the 3/2 power. So that is like a square root of x cubed. Whenever you're given a problem, giving it back in the same form is always a good plan. So this was given to me in square root form, so I'm giving it back that way. So plus 3 times the cubed root of x minus 2 e to the 3x plus c. All right, last one for tonight, or for you guys for tomorrow, I guess. Okay, so I have some trig functions this time. So what I want to do is try and eliminate any fractions with trig functions, and then I have to figure out what trig function has that as its derivative. So if I want to eliminate fractions, then if I have cosine squared on the bottom, then cosine is 1/secant, so it's like having secant squared on the top. So here I have the antiderivative of cosine of 4x dx and minus the antiderivative of secant squared x dx. All right, so now I'm thinking in my head, what trig function has a derivative of cosine? So trig functions are a little bit harder to think about than their algebraic counterparts. So every time I take an antiderivative that has to do with a trig function, that's what I'm thinking in my head. What trig function has a derivative of that? Only helps you if you know the trig derivatives. So make sure that you get those back down if you have let them get a little stale. So you have to know your trig derivatives. So in reminder, if I were to take the derivative with respect to x, if y is equal to sine x, for example, then y prime is equal to cosine of x. So I've got cosine of x, so my antiderivative is going to be sine of x. We have to deal with the 4, so whatever your multiple is, 1 over that in the front. Other thing is that if y is equal to tangent of x, then y prime is equal to secant squared of x. You're not going to have anything at this point that you don't know the antiderivative of, so everything you see in this section should be the answer to one of your derivatives. So this is equal to 1 over the constant sine of 4x minus the antiderivative of secant squared is tangent, so tangent of x plus a constant. So 1/4 sine of 4x minus tangent of x plus c. All right, I'm going to leave it here for now. One thing to know is for attendance, to count as attendance for this particular class period, I want you to write down and turn in this problem. So turn that in on Thursday to count for class attendance for this missed class on Tuesday. So this is everything we would have covered in class on Tuesday, and I hope you have a good couple days, and I will see you with your tests on Thursday.